So, you just got your annual lab results and your total cholesterol is over 200 milligrams per deciliter. But what does that mean? Are you at increased risk for stroke and heart attack? Should you stop eating red meat? Do you need to be on a cholesterol-lowering medication? Over the next few minutes, we're going to look at how lipids, specifically cholesterol, free fatty acids, and triglycerides are handled in the body, the significance of HDL and LDL cholesterol, and show you how to analyze and understand the most significant elements of your own lipid profile labs. This is a difficult topic, so we're going to break it down into two presentations. In the remainder of this video, we'll talk about the biochemical structures of the various lipids, and in the second video, we'll go into some detail about how these lipids are transported through the body. To get started, let's first look at the molecular structure of fatty acids, triglycerides, cholesterol, and cholesterol esters. Fatty acids are energy-storing hydrocarbon chains starting with a carboxyl group at the alpha end, connected to a series of hydrocarbon molecules, the last hydrocarbon always referred to as the omega end of the molecule. Saturated fatty acids have a full complement of hydrogen atoms on each carbon, producing a linear configuration. Unsaturated fatty acids have at least one double bond between carbons, eliminating two adjacent hydrogens and causing the molecule to bend. This is a monounsaturated fatty acid. Additional double bonds produce polyunsaturated fatty acids. The popular omega-3 fatty acids are all characterized by the last unsaturated double bond occurring on the third carbon from the omega side of the molecule. In a polyunsaturated omega-3 fatty acid, additional double bonds can be found closer to the alpha side of the molecule. Fatty acids can be further divided into essential and non-essential. Essential fatty acids are needed by the body for normal growth and function, but cannot be produced by the body itself and therefore need to be consumed in the diet. Non-essential fatty acids can be produced from other nutrient precursors such as carbohydrates. The fatty acids can be further subdivided into medium chain, long chain, and short chain based on the number of carbon atoms in the molecule. Short-chain fatty acids have fewer than 6 carbons, medium chain 6 to 12, and long chain greater than 12. This classification will be important when we talk about lipid transport in a moment. Finally, the free fatty acid is used as an energy source in heart and muscles. However, for transportation and storage, 3 fatty acids are linked to a glycerol molecule to form a triglyceride. The glycerol molecule has a 3-carbon backbone linked to 3 hydroxyl groups. Remember from basic chemistry, each carbon requires 4 bonds for chemical stability, so the other bonds on each of the carbons is provided by a hydrogen atom. Similarly, each oxygen requires 2 bonds for stability, one to its hydrogen atom and the other to the carbon backbone. The free fatty acid is joined to one of the 3 carbons of the glycerol molecule, linking the hydroxyl group of glycerol and the carboxyl group of the free fatty acid through an esterification reaction as shown here. As you can see, in the process, 1 water molecule is released during esterification, and the chemical bond accounting is satisfied with 4 bonds to each carbon and 2 to each oxygen. To complete the molecule, 2 more free fatty acids are joined to the remaining 2 sites of glycerol, producing 2 more molecules of water in the process. Again, this triglyceride molecule is the storage and transportation form of fat in the body. Cholesterol is a unique form of a lipid with a chemical formula of C27H46O, consisting of 4 linked hydrocarbon rings with a hydrocarbon tail at one end and a hydroxyl group at the other. The molecule is called a sterol since the tail is the basis of steroids and the hydroxyl end is an alcohol. In fact, the word cholesterol is actually descriptive. The Greek root chole means bile. As we will see in a moment, cholesterol is found abundantly in the bile, either free or as a precursor to the bile acids used in fatty digestion, and sterol, of course, means steroid alcohol. Cholesterol has received a bad rap over the years, accused of contributing to a multitude of vascular-based diseases, including peripheral arterial disease, stroke, and heart attack. However, cholesterol is actually an essential molecule in animals as both a structural component of the cell membranes as well as a precursor to a multitude of steroid-based hormones in the body, including aldosterone, cortisol, testosterone, estrogen, progesterone, and vitamin D. Cholesterol is also necessary for the digestion of dietary fats, as well as the transportation of fat and fat-soluble vitamins from the bowel to the body. The two most important forms of cholesterol when talking about lipid transport are the free form, as seen here, and the cholesterol ester, basically the cholesterol molecule attached to a free fatty acid. As we saw with the formation of triglycerides, the free fatty acid attaches to the cholesterol molecule via an esterification reaction between the carboxylate or alpha end of the free fatty acid and the hydroxyl group off of carbon 3 of the cholesterol molecule, producing a single water molecule in the process. So the cholesterol esters, triglycerides, free fatty acids, and free cholesterol are the four major forms of fats that we need to metabolize and transport through the body. When we talk about the transport vehicles themselves, we'll describe an essential fifth lipid molecule called a phospholipid. But first, I want to go into some details about the chemistry of solubility. The majority of us take for granted that certain things dissolve easily in water, like table salt. We also know that oil and water don't mix, as the oil or fat is insoluble in water and the lighter fat molecules float to the top, forming a distinct layer above the more dense water. But why is this? To explain this phenomenon, let's first take a closer look at the water molecule itself. We all know the chemical formula of water is H2O, meaning two hydrogen atoms are attached to a single oxygen atom. But this is not a linear molecule. Remember, oxygen has 6 valence electrons in its outer orbit, with 2 paired and 2 unpaired. The 2 unpaired electrons can participate in chemical bonding. To complete its outer orbit, 2 more electrons are necessary to achieve its noble configuration of 8 orbiting electrons. Hydrogen has a single orbiting electron in its lone s shell and needs 1 more to obtain its noble status of 2 orbiting electrons. Alternatively, hydrogen is sometimes willing to be more metal-like and just give up its single electron, completely emptying its single s shell. The water bond is sort of a hybridization of these two states. First of all, the 3 atoms form an angle of 104.5 degrees with the hydrogen atoms asymmetrically positioned on one side of the molecule. With this configuration, we can see that the 2 paired unshared electrons of oxygen predominantly occupy one pole of the molecule. Since electrons are negatively charged, this side of the water molecule is slightly negative. In addition, the hydrogens asymmetrically share their single electrons more with the electrophilic oxygen atom and less with themselves. Since hydrogen has a single positive proton surrounded by a single orbiting electron, this asymmetric electron sharing causes this side of the water molecule to be slightly positive. With a positive charge on one side and a negative charge on the other, water is known as a polar molecule. We can actually demonstrate this polar nature of water with a quick little experiment you can do yourself at home. If you take a glass or plastic rod and rub it with a cloth, you create a static positive charge on the rod as the rubbing action removes some of the superficial electrons on the rod's surface. If we have a thin stream of water from the tap, the thinner the better, and we bring the rod close to the stream, you can see the charge on the rod actually causes the stream to bend. The positive charge on the rod attracts the negative or oxygen pole of the water molecule and pulls it towards the rod. If we allow the water to splash on the rod, the surface electrons are restored by the water atoms and the attraction stops. Rubbing the rod again with the cloth recharges the rod and recreates the bending of the stream. For our discussion of lipid transport, this phenomenon is important because only polar or charged molecules dissolve in water, but nonpolar molecules will not. For instance, we know sodium chloride or table salt dissolves readily in a glass of water, especially warm water. Sodium is a metal in the first column of the periodic table, and chlorine is a nonmetal on the far right side of the periodic table. Sodium, like hydrogen, has a single valence electron in its s shell, and also like hydrogen, either wants to get another electron to complete the shell, or, like the true metal it is, give up its electron and completely empty the s shell. Chlorine, on the other hand, has 7 orbiting valence electrons and desperately wants 1 more to complete its p shell. With sodium willing to give up its single electron, the imbalance of charges makes the sodium atom slightly positive. Similarly, with chlorine's willingness to accept an extra electron, the imbalance of charges makes this atom slightly negative, and the bond between the two is referred to as ionic. In the polar environment of H2O, The oxygen or negative side of the water molecule is attracted to the positively charged sodium ion, and multiple molecules can strip it away from the lattice of the salt crystal. Similarly, the hydrogen or positive side of the polar water molecule is attracted to the negative chlorine ion, surrounding and stripping it away, effectively dissolving the solid into the aqueous environment of the water solvent. Heating the water causes the molecules to move faster, exposing more of the polar molecule to the sodium and chlorine ions, and thus increasing solubility. Fats are composed of carbon, hydrogen, and oxygen, with the predominant chemical feature consisting of linear or branching carbon chains. With the adjacent carbon atoms equally sharing electrons, these molecules are considered nonpolar, non-ionic, and therefore won't dissolve in the polar environment of H2O, but will dissolve in other fats homogeneously. Since fats are less dense than water, they float to the top of the container, separating almost completely from the water itself. Since the plasma of our blood is basically salt water, the fats that we ingest and deliver to the cells of our body need some sort of transport vehicle to get around. Otherwise, if these fats were simply absorbed directly into the bloodstream, they would separate out from the plasma, clog the small vessels of the brain and organs, and we would simply die after we ingested our first serving of ice cream. These transport vehicles are known as lipoproteins and include chylomicrons, very low-density lipoproteins or VLDLs, low-density lipoproteins or LDLs, and high-density lipoproteins or HDLs. We will describe these in detail and explain the biophysiology of lipid absorption and transportation in the second and final video of this series.